Уважаемые коллеги, у нас сегодня делает доклад Ширикян Армен Рафикович, который работает в Парижском университете во Франции. Тема его доклада «Введение в теорию больших уклонений Донскера-Варадана». Ну и я хотел добавить, что у нас также выступал доклад на конференции. Как вы знаете, все те, которые ходили на конференцию, и он является членом нашей группы по мегагранту. Пожалуйста. Это не один доклад, это как называется? Курс
ну, это очередная мини-лекция. Лекция, это, наверное, какая-то 34-я, наверное.
Мини-курс как-то было.
Да. Лекция, да. Моя что Армен сначала был студентом в Ереване, сразу в Москве. И, кстати, получал ленинские стипендии, то есть молодежь уже не знает, что это такое, а люди поставки хорошо знают, что это такое. Вот потом он был, как я, аспирант марковских, который вот на стене слева. Потом самое много работали в Великобритании. У нас 10 статей, одна книга, так что мне вот очень приятно, что здесь с нами. Все равно, пожалуйста.
If you speak English, because at least one person here does not understand Russian, we believe that some people will join us in internet.
Вы когда хотите делать перерыв? У вас же...
Сказали час 15 минут перерыв, еще час.
Да, вот так. Ну, хорошо, рассказали.
Well, thank you very much. So the book will be in English, and it is an introduction to the theory of our deviations, with a special emphasis to the theory of Donskerah-Varadana applied to Markov processes. So I will write here the plan of my talk. There will be 3 parts. I will begin with some generalities on our deviations. Then I will present a general result called Kiefer theorem, which can be applied in many situations. And finally, in the 3rd part, I will concentrate on Donskerah-Varadana theory. Okay, this will stay here for a while. So I will begin with various number of things. But before giving a formal definition, generalities on large deviations. For giving a formal definition, let us consider an example, just to show what kind of asymptotic results we are looking for. Let's consider an example. Let's fix an interval AB. And 2 continuous functions on this interval. So both functions are continuous. And in addition, I assume that J is strictly positive on that interval. And I will also need a parameter n, which will always vary in the set of positive integers.
You use G twice for function and for positive. G is positive function.
G is a positive function.
Okay,
Yeah. So let us consider the following integral. Integral from a to b exponential and f of x, g of x dx. And I want to study the asymptotic behavior of this quantity when n goes to infinity. So there's the product of 2 positive functions. So everything is positive here. Well, it is not difficult to show, and I will do it, that if we take a logarithm here, and divide by n, natural to take global, right? Because we have something which grows exponentially, may grow exponentially. F is a function. Then the limit of this expression, when only n goes to infinity, is equal to the maximum of this function f on the interval AB.
This is how this is. This is what plus.
Laplace type asymptotics, yes, exactly. Laplace type asymptotics. Okay, let's see why it is true. So let me note this expression by an. This expression, by definition, this will be an. So very often when you do asymptotics, you need to derive up and lower bounds, and this is what we are going to do. Well, let me note by n the maximum of the function f. Then obviously an will be smaller than, I just take the maximum here, it will be exponential, n times n, and then I will need to multiply by the maximum of the function g times the length of the interval AB. So let's denote everything by c. C is a constant, positive constant. Then obviously if you take this limit, well, I don't take limit, I take double limit. When n goes to infinity of 1 over m logarithm an, then this will be smaller than m. Right, just taking the logarithm dividing by n, everything disappears, only n is left. So we have now upper bound. Now what about the lower bound? The claim is that if m is the maximum of a continuous function, then I can find an interval, let's denote it by j, AB, it will depend on epsilon. For any epsilon, I can find an interval, non-degenerate interval, or AB, such that f of x is greater than m minus epsilon. Well, I don't put brackets here, m minus epsilon, for any x on j epsilon. Right, we have a continuous function. The maximum is achieved by continuity and so on some interval, it will be greater than m minus epsilon. Then I can do the following lower bound for an. An will be greater than this m minus epsilon, which will appear here, exponential m minus epsilon times n. Then we have g, it is a positive function, so it is minorized by a positive constant. And then we have the length of this interval j epsilon, so everything will be a constant, positive constant time depending on epsilon. Then I can do the same, but now I will take the lower bound, lower limit.
Excuse me.
Yeah.
Would you write down C epsilon?
Sure. C epsilon is the length of this interval, interval j epsilon multiplied by the minimum of the function g.
I think this would be helpful.
Sure. Yeah. So it is a positive number. It may be very small, but still positive. So when we take the limit of 1 over n logarithm an, then this will be greater than n minus epsilon. So on one hand, the upper limit is smaller than n. On the other hand, the lower limit is greater than n minus epsilon. Because epsilon is arbitrary, we get immediately this result. Now, let's assume that here you don't have a function, but you have a sequence of functions, or more generally, measures. I'll assume that you have a sequence of measures which have densities with respect to that measure. And for these densities, I will assume the following. I will assume that Gn of x is equal to exponential minus n I of x. Now, I have the right to do whatever I want. I have a positive function. I can represent it in that form. And here I write just a constant plus small o of 1. and this asymptotic should be true as n goes to infinity uniformly in x.
And what does it mean IX?
Yeah, this is ix is a function where I is just a function. Continuous function on the interval AB. You may think of I to be positive. In that case, on the set when I is positive, this measure disappears. On the set when I is equal to 0, it does not disappear. So actually, you can assume that these are probability measures. So the limit of the sequence of probability measures is concentrated on the set, on the null set of the function I, on the set when I is equal to 0. Right, so you have some concentration of measures. And now you're asking, what is the asymptotic of this integral from a to b, exponential n f of x? And here I have this mu n of dx. Right, we have measures. And we're asking, what is the asymptotics of this integral? So not only you have a parameter here, but you have a sequence of measures there. Well, in this particular case, the answer is not that difficult, because if you put this function here, this one, if you put here, you will have n multiplied by f minus I multiplied by another positive function. Right, so we didn't use anything about this function, just positivity, just to be separated from 0 and from infinity. So if you put that function here, you will have n f minus I and some positive density. So I will not prove it, is just almost obvious that if we take the logarithm here and you take 1 over n, limit as n goes to infinity, exactly the same argument, we show that this is equal to the maximum of f of x minus I of x when x is an AB. And this is exactly this type of asymptotics we are looking for. The difference is that the integrals will be taken in the multidimensional space, or more interestingly, on an infinite dimensional space.
But of course, this looks unnatural, right? Because you have this exponential density. Mu n has density, which of course of the same kind as the function exponent of n.
Sure.
Right? So
Sure.
it is an unnatural example which shows what you want to do.
Well, maybe in this particular setting it is unnatural, but this is exactly what will happen very often with derivations. Yeah, so this has a name, is called Varadan.
Because then of course you need the question, why you do not write an integral mu n as gn of x dx and then just.
Yeah, I could have done it. But just to show that you have separation, you have growing functionals or any functional depending exponential of something and sequence of measure which concentrates somewhere. Now this is how this exponential and concentration of measure, how they interact. So this was just anyway, so this is true, and we can forget about this. Remember just this formula, and this formula will appear in different forms in what will come. Okay, so well, let me give maybe let me give an example, another example what we are interested in. What we are interested in. Example. So let's assume that you have a random sequence. So let's assume that you have a Polish space. A Polish space means that it is complete separable metric space. Complete separable metric space.
And it is Polish, just one Stefan Banach and Lvov, full of mathematics, which essentially created half of theory about this kind of spaces.
And so let's assume that you have a sequence xn, sequence of x valued random variables. Then I can look at the following object. I can look at mu n sorry, for later use, it's better to write here x, but different x. 1 over n.
You should also change
Yeah,
below.
thanks.
Excuse me, tell us again what is RV.
What is what?
RV.
Random variables. Random
variables.
Random variables.
Random. I see.
So I consider direct mass concentrated at the point xt. Right, so I have a random sequence. Then I consider direct mass at the point xk. So this is a measure. Because xk is random, I will have a random measure, and I take this combination of random measures. So this is a random variable in the space of measures on x. So this is probability measures on x. So I will specify a lot of things a bit later, just to get familiar with the object we will be dealing with and writing this example. So this will, I will remind you and with some more information about px. For the moment, just px is the probability measures on x. Okay, so we will be interested. The goal is to find these type of asymptotics when mu n, when this mu n is the law of mu n. It may look a bit ugly because you have a measure, we have a random variable in the space of measures. So the law of mu n is a measure on this space. It may take some time to get used to that, but this is indeed very natural object in the theory of large deviations. So anyway, so just to tell you what kind of asymptotics we are looking for. So we are looking at asymptotics of this kind when it is not AB, but this space Px, and we have measures on this space Px. Okay, so now let me give a formal definition of large deviations. So definition, or maybe I got it here. Okay, right. Definition. I fix space X, which I will assume to be compact now, just to simplify things. This is a compact metric space. And I consider a sequence psi n, which will be a sequence of x valued random variables. And I will say that psi n satisfies the large deviation principle.
They not identically distributed around. So
No, just the sequence. We say that
and not independent.
not independent, nothing, just sequence. Well, think of this. I mean, they are not the law of mu n is a random variable. So our example will be psi n will be mu n. So just the sequence of random variables.
So
We say that psi n satisfies the large deviation principle, LDP, large deviation principle, if there is a lower semi-continuous function I going from x to r plus bar, and r plus bar is a real line plus infinity. So LDP is large deviation principle, LSC, lower semi-continuous function.
Well, could you remind what does it mean?
Yeah.
Because I'm pretty sure that
Yeah, sure, okay.
most people have no idea for what.
The definition,
Because suppose it's tempting to ask why you consider this, why you do not consider just continuous one.
it is too restrictive. Continuous is too restrictive.
What does it mean?
It means that when you have that type of asymptotics, then very often it will be not continuous.
Okay, very good.
Okay, so going a bit further, I can say that if you have what I'm going to write here in a moment, if you have that with some function I, then you will have that with lower semi-continuous function I. This I will make some comments about that. Just
Just remind what does it
yeah,
mean?
yeah, sure. Okay, so we say that we have a metric space, and we have a function from X to R plus. So by definition, this is lower semi-continuous if, now there will be discussion about the terminology, for any C, the set sub-level set, or it is usually called level set in the theory of large deviations, this set is closed. So, okay, let me write that. This means that we are taking those X for which I of X is smaller than C, and the condition is that for any C, this set is closed. Okay, in the case, for instance, when I is continuous, this set is certainly closed, right? Because it is the inverse image of interval from minus infinity to C. Now, allow semi-continuity means this, or you can write it differently. It is a simple property that if xn converges to X in X, then the lower limit of I of xn is minorized by I of X. Really not difficult to show that these two properties are equivalent, and if they are satisfied, then we'll say that the function is lower semi-continuous.
So the function may jump down but never up.
No, or on the contrary, the function cannot jump down. It may jump up,
But no, down.
but not down.
No. Is this I the same as here?
No, just
It's just a definition for I.
I see.
What I'm saying that this I of X, well, it depends what you call the jump. I mean, yeah, sure. Okay, you can say, well, this is allowed. This is not. Okay, now in both cases you can say that there is a jump. Yeah, okay, so jump down. Yeah, okay, you're right. You can jump down, but not up. Yeah.
And can you show us some example which has some sense in your construction of such compact metric space? Which spaces will you use? For example,
Okay, I will use this space right here. X is equal to Px, in which X is compact, well, compact metric space. And then P of X is the set of probability measures on X. I need to specify the topology. Topology is weak star topology, weak star topology on Px, on this X, which means that by definition, mu n converges to mu if and only if for any continuous function. So we are in the practice, so I don't impose the boundedness. For any continuous function, integral of f d mu n converges to the integral of f d mu. So this is the definition of weak convergence of measures. And this topology can be metrized. Well, maybe I will tell about it later. Well, okay, so we can do it immediately. So let's denote by Fn. So if Fn is a dense sequence, sequence in the unit ball of Cx, then the distance between two measures can be introduced by this formula, integral n from 1 to infinity, 2 to minus n, and the difference. Okay, I write like this. F mu minus F mu, and I take the absolute value of the difference. Okay, so I hope this is visible. What I'm saying is the following. So you have a compact metric space, for instance, interval 0, 1. You consider the space of continuous functions of that compact metric space and the space of probability matters.
To clarify the definition, is it allowed the function to have different left-hand limit and right-hand limit at the same point?
Yeah. Yeah, you can have different limits from left and right.
And the right limit may not exist. Right?
Yeah, a limit may not exist. I mean, you can have a low limit, a left low limit may be different from right low limit. I suppose this is what you meant, right?
And vice versa.
Yeah, okay, so, well, we won't be dealing with intervals, it will be just abstract metric space. So I think this is a thing about in terms of goals.
I'm just trying to figure out what is the difference between low semi-continuous functions and up semi-continuous function.
Well, upper semi-continuous, you just put upper limit here.
Yes, I mean in the pictures.
Well, this one is lower semi-continuous, this one is upper semi-continuous.
Ah, I see. And nothing about the case where the left-hand limit and right-hand limit are different.
Okay, so let me do like this.
Ah, the same.
Yeah, so.
Yeah, which one should be upper than another one?
The limit, the value of I at the limit point should be lower than the low limit. Here, the value of the function at the limit point should be upper than the upper limit.
The main point is the difference between the value of the function and
the low limit.
Yes, not between the limits from different sides. Oh, it is clear. Thank you.
Okay, now let's go back to this. We will do this anyway, so let me finish now. Let me finish.
Okay, so just remarks. So if X is segment 0, 1, right, that the space of measures on 0, 1, classical logic from 19th century, and then it's the result of RIS that is called, it is 100 units. Space of measures on the segment 0, 1 is a compact space.
Yeah. Yeah, I don't know who told that. Yeah, definitely studied that question. The dual space of the continuous functions and
In this case, yes.
Yeah. Yeah, that's just 1 second. So I think in the compact case it is in the compact case it's not that difficult, right? So you can use the subsequence and then approximate, I believe.
Since it is 100 years old, not.
Yeah. So anyway, if we have a compact metric space, we can actually use the big topology, which means that the average of any function with respect to mu n should converge to the average of that function with respect to the limiting measure. And that convergence, for the moment I just introduced the concept of convergence, it is not difficult to show that if you choose any dense sequence in the unit ball of Cx, centered at 0, of course, then what is written here, so 2 to minus n, well, of course, you can put any decaying sequence so that series converges. And I took the difference. So F nu is this. F nu is this. Right? You take the difference between mean values, absolute value of difference, and multiply it by decaying factor. So this is our main object. So even though many results will be formulated in terms of the abstract metric space, I will be mostly interested in this particular situation. For instance, Hilfer theorem and Donsker-Varadan theory is about this type of
Yes, and Hilfer planned to come to this conference, but due to unfortunate events in Israel, he canceled.
Okay, now let's go back to the definition of large deviations. So say that psi satisfies the large deviation principle if there is a lower semi-continuous function I from x to r plus bar, such that there will be long inequalities. I will write and then we'll discuss what is written there. So I'm taking the lower limit as n goes to infinity, 1 over n logarithm probability that psi n belongs to gamma. I need to say who is gamma. This is certainly smaller than the upper limit as n goes to infinity, 1 over n logarithm probability psi n belongs to gamma. So whatever this means, this is always true. Lower limit is always smaller than upper limit. Then the key things are here. This is greater than minus infimum of I on the interior, and this is smaller than minus infimum, it is indeed infimum, not a supremum, of I on the corner. And this should be true for any gamma Borel subset of X, where gamma dot, gamma bar is the interior or corner of gamma.
Armen, can we replace here just this set of Borel subsets by set of open subsets? It will not be theoretical. You see, you said Borel subsets. I'm pretty sure that not everybody remembers with the guys.
Yeah, you can, because well, in fact, this is equivalent. So let me give a number. 1 is equivalent to the following. For any G which is open, this part is true. Lower limit as n goes to infinity, 1 over n logarithm probability psi n belongs to G. This should be greater than minus, let me introduce another notation, and this will be the last one, there will be no more notation. And for any f closed, the upper limit, 1 over n logarithm p probability of psi n belongs to f is smaller than minus I of f, where I of something is the infimum of I, that's f. Okay, so this is the definition of large deviations. Right, so this is the definition of large deviations. Oh.
The second case,
Now I think that
upper limit, in second case.
in the second case upper limit. I'm saying that 1 is the same as this. Why? Because, well, this is always true. If I replace gamma by its interior, I will have something which is smaller, right? The probability of belonging to a bigger set is bigger than the probability of to belong to a smaller set. So if I replace this gamma by its interior, what I will get is smaller than this lower limit. And if this is true, then this inequality will be true. And the same here.
Does number one refer only to one inequality or to the whole rectangle?
To the rectangle, yeah. And in fact, this is what is you should prove when you are doing large deviations. You should prove upper bound and lower bound. And in what follows, to simplify notation, if you have this, the lower limit on open set is minorized, upper limit on closed is majorized, I will say by definition, I will write that the limit 1 over n logarithm probability psi n in gamma is equal with the dot above minus I of gamma. So when I write this, just by definition, it means that you have this for open set, this for closed set. Right? Not to write each time both bounds.
This is no notation, right?
This is just a notation. It has no meaning. The meaning is here. Just replace 2.5 by.
If the function I was continuous, then all this gain would not be needed because then the left object and the left would be equal object to the right.
No.
No, why? Look, if I was continuous.
Yeah, but I mean, this the interior may be empty there, while the closure is non-empty.
What is that enclosed? Okay, right. Okay.
Yeah, in all these cases, I forgot to say that the infimum. Yeah, well, I don't need it, but when there is an infimum over R empty set, then it is plus infinity. So convention, not to forget. You don't feel it's for the moment. The logarithm of 0 is minus infinity. Infimum of anything on a closed set is plus infinity. Okay, so in particular, for instance, if the interior is empty, we have infimum of I over empty set, it is equal to plus infinity. So this we will have minus infinity. So the left, the lower bound is empty. There is nothing. Okay, let us consider an example. Let us consider a trivial situation when this set X, which is in general compact matrix space, is just a finite set from 1 to n. Now, it does not make much sense to study large deviations here because there is not enough space to deviate. But still, you can formally write the definition. The claim is that, okay, so you have a sequence, x-valued sequence. So x-valued random sequence. Then the claim is that psi n satisfies large deviation principle. I forgot to say one thing here, that this function I is called range function. Definition, I is called the range function of the large deviation principle. And in general, if I have a lawfully continuous function with range in R plus bar, then I will call it a range function. So then this sequence satisfies the LDP with a rate function I, so we can write once again that it should go from x to r plus bar. This is true if and only if for any j in, okay, let me write like this, 1n. This means I take only the integers belonging to this interval. The limit as n goes to infinity of 1 over n logarithm probability psi n equal to j is equal to minus I of j. So now it is indeed in quote, it's not just a convention. The claim is that if you have this discrete space, then validity of large deviation with some rate function I is the same that validity of this for any j. So why it is true? Let us remark another remark here. A remark. If by chance these two quantities are the same, may happen. If I of gamma bar is equal to I of gamma dot, then you just have a limit. Limit n goes to infinity, 1 over n logarithm probability psi n in gamma is just equal to minus I of gamma. Just a trivial remark. So if this is equal to that one, then that all limits are the same and you have a limit. Now, this may happen when a set gamma is at the same time closed and open. And this is exactly the case because we have a discrete topology. So if we have large deviation principle, then you certainly have this. Now, for the implication in the other direction, I will write a small lemma, which is almost obvious, and then you will tell me if you want me to prove it. So suppose that you have two sequences of positive numbers, such that 1 over n logarithm I a n converges to a, and 1 over n logarithm b n converges to b. I take two sequences, a and b n, such that you have these limits. Then, right? Then, if I take the same expression for the sum, a and b n, you will have the strongest sequence will win. You have the maximum between a and b. And I claim that this lemma,
Limit problem.
yeah, limit. Thanks. This lemma combined with this equality implies immediately large deviation principle. Now, if it is okay with everybody, I will skip the proof of this lemma. It's really not difficult.
Yes.
And then if you write here psi n belongs to gamma, gamma is just a finite subset here. Right? So if gamma is a finite subset, then 1 over n limit of 1 over n logarithm p psi n in gamma is just, I can write this probability as 1 over n logarithm and sum of probabilities. The sum over all j which are in gamma, probability that psi n is equal to j. Now, of course, the lemma is true not only for two sequences, but for any finitely many sequences. So if you have k sequences and you take the sum of k sequences, you will have the maximum of all the limits. And now we have exactly that situation. These are your sequences for which we assume that there is a limit. So this one will be the maximum of those limits. Maximum when j is in gamma of minus I of j. And this is exactly minus I of gamma, because I put the maximum becomes minimum, and this becomes I of gamma. So for finite space or finite metric space, you have our relations if and only if you have this equality for all elements of the cycle of the space X. All right. Oh, okay. So, well, in this introductory part, I will prove 3 results of our relations. Well, the first of them, the simplest one, is called contraction principle. It is a name, contraction principle. So you have to clarify things. It has nothing to do with what we used to call contraction principle when we were students, right? So it is not Banach contraction principle. It is about the image of sequence satisfying the LDP. So let X, Y, to simplify things, I mentioned that these are compact metric spaces. And let psi n being X valued random sequence satisfying the large deviation principle with a rate function I. So it is a function from X squared plus. I have 2 metric spaces, and I have a sequence, random sequence in the first of them, which satisfies the large deviation principle with some rate function I. So let phi be continuous map. Then phi of psi n satisfies the LDP with the rate function, which can be written explicitly, j of y is equal to the infimum of I of x, and I'm taking those x for which phi of x is equal to y. Or I can write it differently. It is I calculated on the inverse image of the set consisting of 1 point y. Okay, so you have one metric space x, you have another metric space y, and you have a continuous path from the first of them to the second. If you have a sequence living here, which satisfies the large deviation principle, then the image of this psi n by the function phi, which lives in the space y, satisfies the large deviation principle, and you can write, well, not an explicit formula, but something like that, for the rate function of the image. Now I will prove this result. Or maybe before proving that, let's go back to that example. Let's consider that like the object, right? So you have a sequence of random measures. Or for the one, let's assume that you have random sequence in random sequence in P of X, in X, which is now P of another space X. Now I want to construct my continuous function. So I construct the following continuous functions. I take a function f, which is a function on x, and I construct the function phi, which depends on f. It acts on this space, on the space of measures, with range in R, so this is f, and it takes a measure mu to the mean value of this function f with respect to this measure mu. Yes, I have a random sequence in x. I have a continuous function on x. I have this map, it acts from the space of measures in R. It takes a measure mu to the mean value of this function, which is fixed with respect to mu. So this is a function from x to R. So if I know that mu n satisfies LDP, then phi mu n also satisfies LDP. And in particular, if I take these type of measures, if my mu n is the time average of Dirac masses, also called empirical measure of the sequence xk. So xk is a random sequence with range in x, usual x. Then this mu n will be a random sequence in the space calligraphic x. So if you have this delta xn, then if I take f mu n, what I will get? Something which is much more intuitive. You get k from 1 to n, f of xk. So think of a Markov process living in the space x. You are interested and you have an observable. You observe this Markov process by your function, continuous function f. You are interested in the behavior of the time average of this observable on trajectories. Right? And this is what you need to study, right? You want to study time average, you want to understand if you can say something, about the law of this sequence. Now the claim is that if you know something about mu n, then you will know something about f mu n, which is the object of interest. So this is why studying the Sartre object makes sense, because once you have that, once you have the result for that, you will have whole bunch of results for any continuous function, or maybe even more, because this contraction principle has generalization for functions which are not necessarily continuous. Yeah, I want to emphasize that this is indeed continuous function, right? If mu converges to mu n converges to mu, we have weak topology, weak star topology, then f mu n will converge to f mu. So f mu is continuous. It is continuous. So let us now prove this result. It is really stock result. So what we need upper and lower bounds. Right? So large deviation is the same as its upper and lower bounds. So what we need to prove, well, there are two things to prove, right? Large deviation upper bound and large deviation lower bound. Let's begin with large deviation upper bound. Let's fix a set F. I'm looking at the upper bound. I need to say fix the set F, which is in Y, and it must be closed. And what we want to prove is the following: upper limit.
You're going to use 2. This one is equivalent to, right?
Yeah, I'm going to use this to this. Yeah, I'm going to use this. Let's give a number. Yeah, let's give a number 2. So upper limit of 1 over n logarithm probability psi f of psi n belongs to f, this should be smaller than minus this new function j calculated on it. So this is what I want to prove. But let's see what is written here. The probability that phi of psi n belongs to f is the same as the probability of the following event. Psi n belongs to the inverse image of f, inverse image of f by this continuous knot f, phi. But this one is closed because phi is continuous. Therefore, I can apply large deviation upper bound. One over n, logarithm probability psi n belongs to phi minus 1 of gamma. So this is smaller than what? Smaller than minus I of phi minus 1 of gamma. Phi minus 1 of f, sorry. Phi minus 1 of f. It remains to show that if I define j by this formula, then I will have exactly this expression. So it remains to prove that if I define j by that formula, then I of phi minus 1 of gamma will be j of gamma. For any gamma, in fact, this will be true for any gamma subsetting y. There is no measurability, just functions, just infima. Okay, let's see why this is true. So what is written here? Phi of phi minus 1 of gamma is the infimum of I of x when x belongs to phi minus 1 of gamma. Right? Or it is the same as the infimum of I of x for those x for which phi of x is equal to belongs to gamma. Or I can write it some bit differently. I can write it that this is the same as the infimum when y belongs to y, and infimum when x belongs to when phi x belongs to y. Phi x is equal to y. And I take here I of x. Right? So having the infimum of I of x when phi x belongs to gamma is the same as the having first infimum over those x for which phi x is equal to y, and then taking infimum over all y which is in y capital. Right, so then I have two infima. Again, I can do like this. But what is written here? No, it is not gamma. It is not y. It is gamma. So what is written here is exactly by definition j of y. J of y is the infimum of I of x and phi x is equal to y. So this gives the results for this gives the upper bound. The lower bound is exactly the same because if you have here open set, then phi minus 1 of g will be open set, and you can repeat the argument. So the lower bound, the proof of the lower bound is similar. Okay. Let's move to the second result. Second result, here in 2. Well, it has a name, it's called Varadan lemma. Again, I will assume that we are working in a compact metric space. So let X be a compact metric space. And psi n a random sequence in X satisfying the large deviation principle. With the rate function I. Then, for any continuous function on X, let's call that X is compact. So if you are continuous, then if F is continuous, it's also bounded. You have the following. I take the limit as n goes to infinity, 1 over n logarithm, and I'm taking here the mean value of exponential of n times f of psi n. And this is equal to the supremum when X is in X, f of X minus I of X. Well, you notice immediately that what is written here is the same as there, except that now AB is replaced by the metric space X. And why this is the same as this one? Because if we denote the remark, if I denote by mu n, the law of psi n, then this mean value, exponential n f of psi n, can be written as the integral over x, right? Psi n is a sequence of random variables with range in x, so the mean value by what's called the transfer theorem can be written as exponential n f of x mu n of dx. We have exactly the same object as written here, but the measure lives in an infinite dimensional space or in a compact metric space, and integration is taken over that compact metric space. So Varadan lemma says that if you have large deviation principle, then you can have this type of asymptotics, Laplace type of asymptotics for sequences, for functions calculated on the sequence satisfying the LDG.
So this was your second example at the very beginning, right?
Yeah, the example is still there.
And how to say that this is a generalization of that example? Just
Well, here you had a sequence of measures, and for that sequence of measures, you had this type of asymptotics. Right? But what does it mean? It means that the probabilities, having this type of probabilities, right? So having that, saying that 1/n logarithm probability psi n belongs to gamma behaves as minus I of gamma, it is the same as saying that the probability psi n in gamma behaves like exponential minus I of gamma multiplied by n. Right? Or, but what is written here is exactly the law of gamma. Saying that the sequence of random variables satisfies the large deviation principle means that the law of these random variables behave exactly the way written here. Of course, it is not exact statement. I mean, you don't need to have a density. Even if you have a density, you don't need to have that type of asymptotic, but it shows the similarity. Well, in principle, so we have to stop at 20 past, right? 15, okay, yeah. 15 past. 15 past. Okay.
Какой посла?
Yeah. So let me give a brief proof of that.
Sorry, but why do we use compactness in the first theory?
Which theory?
In the first theory, where did you use compactness?
We don't.
Okay.
We don't. Yeah, that first theorem is very soft result. And this, well, I have chosen to work in compactness because there are some stuff. For instance, this one won't be true like that. If you don't have compactness here, you will need to assume something more. You will need to assume that, but I don't say what it means. You will need to assume that this sequence is exponentially tight. But I don't do that.
so up to now we didn't use compactness at all.
Up to now, I didn't use compactness. Definition of large deviations in the general case is exactly
Yes.
the same. And the first term is true in this statement without compactness.
Yes.
This one is not. You need some more condition.
Then of course, if you are working as partial differential equation, we never had compactness then.
Well, it depends. I mean, if you are working with a PDE with bounded noise, then if it is by chance the
Right.
PDE is parabolic, you will have a compact absorbing set, and you can.
We use so-called good rate function, and then I will set it constant.
Here, that's something. That's the definition.
Yeah, in this setting, all rate functions are good because we have
Yeah,
compact.
he already function are good in general, it's not the case. So.
By the way, quarter past one is not a circle how. You can break whenever it is convenient for the logic of your lecture.
Yeah, thank you. So in fact, I won't prove the theorem in the general setting. It is a bit technical, but I will prove the theorem in that particular setting just to feel how this quantity appears. Proof in the case x equal 1, n. Basically, again, we will use this lemma, so let us write this expectation. So,
Proof of what, Armen?
proof of this theorem.
Of Varadan.
Varadana lemma, yeah. So we have expectation exponential of n f of psi n. This is the same as the sum a from 1 to n. I'm taking all possible values of the random variable psi n. So I'm taking the expectation. I take the indicator function of the set consisting of 1 point psi n and exponential n f of psi n. I didn't change anything. I just wrote that having this is the same as listing all the elements of the set X and taking all possible values of the random variable psi n. Now, but what it's written here, it says that psi n, this is 0 and psi n is different from j, so I can replace here psi n by j, and I can put this in front of expectation, and expectation becomes probability. This is the sum, j from 1 to n, exponential n f of j, and then probability that psi n is equal to j. But in that setting, knowing large deviation means that those probabilities psi p psi n equal to j behave like exponential minus I n j plus small o of 1. So this is equal to the sum j from 1 to n exponential n.
The upper limit of summation should be n plus, I think, right?
Yeah, it was n here, and should be the same in there. And then we have here exponential minus n I of j times 1 plus small o of 1. Of course, small o of 1 depends on j. But now what we have exactly that situation. So we have okay, let me write one once again. J from 1 to n exponential n f of j minus I of j plus small o of 1. Now we have capital N sequences, and each of them satisfies the following property. If you take the logarithm and divide by n, so you will get this expression, you will have a limit as n goes to infinity. Which means that if I take here the logarithm, exponential mean value of exponential n f of psi n, and I divide by n, then these will converge according again to that lemma applied to n capital terms to the maximum of all the limits. But what are the limits? Limits are fj minus I of j. The maximum j from 1 to n f of j minus I of j, and this is exactly the supremum of the difference f minus I calculated on x. This completes the proof of parallel lemma in this particular case. Well, in the general case, it is this type of argument, except that it is technically more complicated. You need to distinguish between you need to calculate upper limit of this expression, lower limit of that expression. But the idea is here. You do various approximations and you get the result.
Yes, so finite set is not that different from efficiency.
Yeah, at least ideologically, this can also not the same. Well, I think this is a good point.
Yes.
Что, делать перерыв? Сколько? 5 минут делать?